Alright, welcome to day 4, triangle proportionality. Really quick on the warm-up, I am going to go over this one because you are talking about parallel lines and the proportionality of them. That if we have, for instance, these three parallel lines here, which are streets, we are going to have a proportion established between the spacing of these parallel lines. And that's safe to assume. That's actually a theorem. We're not really going to get into the proof of that. But anyways, x will correspond to 16, and 26 would correspond to 13. All right, if I was doing this problem, first thing I would do is simplify 26 over 13 to 2, and now multiply both sides by 16, and I get x equal to 32. And if I look at reference back to the figure, yeah, that makes sense. It's a little longer than 26, so 32 seems like an appropriate answer here. Going on to the next one, the ratio of how far apart these lines are, they're actually the same distance apart on each of them according to the bottom transversal. When that's the case, you can assume that the spacing between the parallel lines will always be the same. It has to be, actually. So we would know that the 3x minus 7 equals the x plus 5. So as far as calculating for x now I can set it up that 3x minus 7 would equal x plus 5. And just going to solve this one really quick. And x equals 6. And now to do the y, I can set those equal. That 9y minus 2 equals 6y plus 4. And so solving that one out pretty quick. Adding 2 and dividing by 3, y equals 2. So the spacing of parallel lines is always kind of special like this whenever you do have parallel lines. You can't make the assumptions I did here without them being parallel lines. That was dependent upon them being parallel. So with example 1, what we're getting into is triangle proportionality. You can see the parallel lines there again, and this is where the transversals are converging at point B. But what happens is we have similar triangles, and you'll see that you actually have corresponding angles, angle BYX and angle C. Also, you have corresponding angles BXY and angle A. So these triangles are similar, so a proportion is true. The cool thing is where before I would have set this up as x being divided by x plus 6, you actually don't have to do that. You can just do x divided by 6 equals 10.5 divided by 4. You actually don't have to add for the whole side here, and it actually works out just the same. Personally, I'll go ahead and cross multiply. Why not? 10.5 times 6 ends up being 63. And dividing now by 4, and that's going to be 20.75 for my x. Alright, and there's my answer. You're probably sitting there like, whoa, that was a bad job, Mr. Bumgarner. You miscalculated 63 divided by 4 horribly. You would be right that that's 15.75. My mistake. Thanks for your patience there. Alright, this problem is actually kind of the converse of what we just did. So we're wanting to know if segment WX is parallel to segment AY. To do that, I'll actually make proportions and compare them. So if I do 18 divided by 32, I'll compare that, and I'll do 15 divided by 25 and see if they come out to the same ratio. If they do, those lines are parallel. If they do not, they're not parallel. For the 18 over 32, I know I can divide out a 4, no, excuse me. I can actually divide out a 2, so that's 9 over 16. For the 15 over 25, I can divide out a 5, so that's 3/5. Since these ratios did not match, I know that the lines are not parallel. If the ratios had matched, then they are parallel, and that's due to the similar triangles that would be going on. Now, looking at those last couple problems leads us right into what's called the triangle midsegment theorem. With that, a midsegment connects two midpoints of a triangle. When that happens, a couple special characteristics occur. First of all, the midsegment will always be parallel to the segment it's not intersecting. So in this case, you can see that segment JK is parallel to segment FG. Another special relationship is that since these were midpoints and they were HJ is half of FH, HK is half of HG? Well, this is actually going to follow that same ratio, that JK has to equal 1/2 FG, and you can see that written right here. All right, here's our last example in figure DE. Segment DE and segment EF are midsegments of triangle ABC. It wants us to find AB. To do that, I'm going to refer to midsegment ED. That's the one that has a relationship to segment AB. Since ED is 5 units long, I will double that to get AB equal to 10. So I'm going to make that note really quick. AB equals 10. Again, that's by doubling segment ED. Moving on to part B. Find FE. Well, if I look at FE, it's a midsegment. The segment of the triangle it's related to is segment BC. Since segment BC is 18 units long, FE needs to be half of it, so it will be 9 units long. And last one it wanted me to do is find the measure of angle AFE, this angle right here. Now, it might look like you really don't have a lot of information there. Some people might start taking 87 off of 180 to get this angle, but that wouldn't really help. The important thing to remember here is that midsegments are parallel to the segment of the triangle. They don't intersect. So since that's the case, 87 and angle AFE, those are alternate interior angles, so they are congruent. So I'm actually able to make that conclusion. The measure of angle AFE is equal to 87 by alternate interior angles theorem. I'm actually done with this example. All right, that wraps up the lesson. I know it was a quick one, but we also got the assignment check on this day. So if you have any questions, please let me know.